Well, thank you everybody for coming to my session on handwriting recognition for the New York Times crosswords. So a little bit of context about me before we get started on what this all is. I'm a games engineer at the New York Times. I work on platforms such as our crosswords, and I work on the team that produces Wordle, Connections, Strands, Pips, a bunch of new games, a bunch of games that we've come up with and that people play from all around the world. So prior to this, I worked at the NBA, working on live streaming platforms, Business Insider, and MTV. So my background is mostly in the media space, as it is at the Times right now. Inclusively, prior to my actual application development background, or in addition, I have an AI and ML background, which I've had for quite a while in traditional ML and AI. So some of that leads into the talk that you're about to hear. And there's some of my socials here, in case you want to connect. So a little backstory to the project. This effort started as a part of what we call Maker Week, which is our internal hackathon that lasts for a week, where people can come up with interesting projects, interesting ideas, and like potentially road-mappable projects. This was from a few years back, where people are interested in using a stencil to write on the New York Times crossword app. If you're an iOS user of our apps on the crossword, there was some level of handwriting recognition available, but Android support was not present, and primarily being an Android developer on the platform and working on the application, it would be a little trickier to get that implemented. But it was started as a fun project, and then it turned into a good learning exercise, and then it actually produced a bit of interesting research in the area of handwriting recognition. So before I continue, our games team, specifically the folks on the Android side, are the true heroes of the New York Times Android mobile app. I am currently on a different project right now, but these are my friends and colleagues, Katie, Lauren, Joanne, Vanessa, Vasil, and Ihor, and they work on, if you're a fan of our games, you can enjoy our games because of their huge efforts on Android. And iOS also has a team. So let's talk about straight away what the problem is. And it sounds straightforward, but actually it gets a little bit into the weeds. So the crosswords as existed before allowed the ability to only do text input via custom keyboard. So this soft keyboard is one that we built, and you could input characters from this keyboard. And I don't know if the actual visual is going to play here, but basically what it looks like is, if it does play, is that the characters get emitted onto the keyboard, and you get to see the output. Part of this, let's see. So in order to have the ability to write in these squares, we added a tiny canvas to each of the letters and the input boxes that you see here, and implemented a touch point tracking algorithm. I'll go into the details about that in a bit. But after writing is done, the canvas's data is converted to a bitmap and sent to a machine learning algorithm. So what you'll see is that, and again, if the visual does actually appear, which again on PowerPoint, there's a little issue sometimes, you need to let the system know that the user was done writing. This is tricky because essentially people have different writing capabilities and writing styles and writing timings. And so in order to partially solve this, we used what's called a mutex. We called it a mutual exclusion lock. That's similar to the way that you would do in the world of threading. But this is also tricky because people have a different type of reset timing for when they enter a letter. So if they lift up their stylus, as you can see on the box on the right, if you do it too fast, then it's not going to necessarily capture all of the pen strokes and form the correct word or correct letter. And all of this work that we're doing, it needs to be user tested more, but for the context of this application, the timing seems to work out, but I'll get more into the details there later. So a little bit of code on the right. I'm not going to get too deep into all the details, but this is essentially a soft lock and release mechanism, which takes in, if you're familiar with Android development and coroutines, it's essentially a way of taking a thread that checks in the background for whether an input has been made, and then waits a few seconds, 2 in this case, and then allows more input into that box that you saw. So basically, we have a touch event. Like if you are touching at any point on that box, that kind of triggers whether you can write on that square. And so that touch event essentially is where this lock gets actuated and allows you to be like, oh, okay, here's a place where I can put another pen stroke within the time. So you have to be a little fast about it. And then you have a release mechanism, which allows that to then lift again for if you're truly done writing the character. So this is the architectural components of this system. So you have a finger down, finger drag, finger up stylus listener. And you have a canvas square, as I talked about. So this is on the mini crosswords. We have the mini crosswords, we have the full crosswords. The reason I chose the mini is because the mini crosswords, if you're a fan of our games, has a big enough square to be a good test bed for this. But the actual crosswords requires more work. And then because this is an AI talk, an AI custom model we built, we needed a algorithm and process to download the model and then actually take the image data and send it to the model and produce a text output. So that's basically that seems pretty straightforward and like a solved problem, but because OCR has been around for a long time. But in our particular case, is actually more challenging, and I'll go into why. But first, before we go into the details of that, I'm going to talk about so-called relaxing conditions. And what that means is that relaxing conditions and pre-processing. So we have certain cases, we're not looking for like very complex handwriting right now, what they call connective cursive. We're looking at straightforward letters with some variation in the letter space. And what we have to do in order to produce those letters is that we have to create a pre-processing algorithm. And so this pre-processing algorithm is, as you can see, steps on the right. You take an input image, you denoise it, and you binarize it, which means you take the grayscale out and just create a threshold for the black pixels versus the white pixels. And then you anti-alias the image, so you can make sure you get the smoothness out of the character so the machine learning algorithm can understand what the character looks like. So actual OCR actually can be quite involved, and I'll go into more into why that occurs. So the first, I'm going to speed through these parts a little bit because I'm going to get to the meat of this because this is actually part of a larger presentation. But we started initially investigating with classical edge detection, rudimentary k-nearest neighbor classifiers, and we went from that. We went to Google ML Kit, something that comes on the device already, and then we tried to do a custom machine learning model, which is what I'm going to be talking about now. And that used a convolutional neural network. So I don't know how many people are familiar with that term. If you're not, then that is a particular neural network that's geared towards image recognition and digit recognition. So start off with classical edge detection. I built a classical edge detection filter system on the right to demonstrate what that looks like for those not familiar. But classical edge detection is specifically around thresholds and looking at boundaries of images to find what could be good features or feature spaces for an algorithm to track, to be like, okay, this is a letter or this is a different kind of image. So basically classification. And as you can see, this is kind of, if I put up an image of my own headshot there, this is kind of what that does. And similarly, if it kind of went past it's a GIF, but similarly, I would do the same to the actual letters, and it would show the edges of those letters. Now, essentially, this falls under a process called canny edge detection. And canny edge detection is good. It is not really the best for the modern day, especially with a lot of variation in your input letters or words. So essentially what happens is that you find letters and then you create what's called a clustering space, and you create clusters. And so this algorithm on the right, which I put together, does the threshold detection. And it's okay, but ultimately, it's not sufficient, and I'll show you why visually. So basically, this is what it looks like between a good edge detection clustering algorithm and a bad edge detection clustering algorithm. What happens is if the letters don't have a ton of variation between them, the letters are great, and they can be separated into their individual clusters. But if the letters have a lot of like interspersed variation, then clustering fails because, as you can see on the right, the clusters actually start to merge together, and an algorithm to detect differences between letters becomes confused. And so that would be why classical edge detection doesn't work so well. And this is, again, I don't know if this GIF is going to fully play, but what you would see here is that the letters actually don't render well on this image. And you'll see like mistakes and other things in the actual output. So what we moved to next was we were using Google ML Kit. And Google ML Kit is great. It's really powerful now. 2 years ago when we first implemented it, it was not sufficient to actually solve this problem. So the good thing about it is if you don't care about the model mechanics or the mathematics, you can use ML Kit to do good digit recognition right off the bat. But again, at the time we were doing this, it was not sufficient at all for what we were doing with the crosswords. And just a little bit of the client-side integration for that, it's actually pretty straightforward. That's why a lot of people like it. And all you need to do is add a listener, download a model, and there you go. You don't have to do all the stuff that I'm going to get into. And again, the performance, if the GIF doesn't play, is so-so. You'll see the letters being entered, but they're not that great. And so ultimately, you'll see like mixed results with recognition. So finally, we went to a TensorFlow Lite model, which is Google's framework for Android and iOS devices to take a machine learning model and put it on the device. And the way we did that is we worked with Google Colab and Jupyter Notebooks. I don't know how many people are familiar with those, and few people might be. You can build a machine learning model in those frameworks and then pull them via TF Lite onto your device. Also, if you're interested, there's tons of free models out there for other things besides handwriting recognition. So it's a really good platform, but this is the architecture on the right. So the first thing we have to do is actually train the model. And the simplest text recognition task is digit recognition 1 through 9. And so digit recognition, has anyone ever done an ML course, is a canonical machine learning task. Everyone kind of goes through it. In our case, it's a little bit more complicated, and I'll again go into why, but the digit recognition problem was most effectively first solved in the late 90s by Linnet and the convolutional network model at that point. Again, it's easier than full letters because it's digits. You don't need the full set of letter data. And in order to do this task, we used a digit data set called MNIST, which has about 60,000 characters. So this is basically the structure of the convolutional neural network, for anyone not familiar. Convolutional neural network is, in my opinion, a magical piece of technology. You send an image to this network. This image then is broken down by the network's components, which are called convolutional layers. The convolutional layers automatically detect what's in the image. So you actually don't have to provide a ton of intelligence, except maybe some pre-training to the image. And then the classification between different kinds of images is automatically learned. And why this is magical is because, again, back in the day when people were doing image processing, they were creating very custom filters to do image processing, writing these very complex algorithms by hand. But when the convolutional net came by, and then in 2012, when the AlexNet ImageNet challenge was essentially solved, that computer vision was basically a solved problem. And so with a pretty straightforward model, you can do almost all computer vision tasks. And so there's a lot that goes into this. We talked about pre-processing. As I showed you, those images are grayscaled down. We send that over to the convolutional network, which mixes and matches input and output data and sends it to a standard neural network, which is this dense layer section here. And these cascading layers, essentially adding more layers produces better results. So we needed a complex layered network to create this handwriting recognition possibility. And these are the types of layers in there for anyone interested: convolutional layers, pooling layers, and rectified linear unit dense layers. And so those structured together allow for handwriting recognition to occur, or any recognition on images to occur. This is an example on face detection. So the idea is low-level features, mid-level features, and high-level features. This network that I showed you here breaks down those features into, does the same thing for faces and breaks faces down to things like curves of faces, then maybe eyes, nose, ears, and then high-level features, which include all different kinds of structures of the entire face. So on the client-side level, we take the model we built on TensorFlow, we pull it down into the client code on the device. That's this client code. and then we can run the model. The model is actually pretty small, about 100K. And this simple convolutional neural net, this is the Python code. So I just want to clarify that there's two kinds of code involved. There's Python code, and then there's Android native Kotlin code. The Python code is where we build the model, and this is the neural network model for anyone who's interested. And in the Kotlin code, which I showed you before, is where the code actually runs on the device. The GIF is not going to play, unfortunately, but basically, this is showing the training of it, and that training is about 98%. It says we're doing really well, but that's actually a suspect number because we essentially weren't able to get good recognition. In the GIF, it would show that you actually are able to get like almost no classification off that. So like an A, entering an A would produce a 9, entering like a C would produce an 8 or something like that. It would be completely messed up. And the problem is that in order to allow that to work properly, you can't, 60,000 characters, as I said in the previous data set, is not sufficient to give intelligence to this model. What you need to do is actually produce, again, I don't know if the GIF's gonna run. No, probably not. What you need to do is build a synthetic data set. So anyone familiar with synthetic data? Yeah. Synthetic data means taking my digits and applying algorithmic affine transformations to stretch the data, to twist the data, and to add noise to the data to make artificially inflated additional numbers to make my classifier much smarter. And basically, you can warp these numbers, rotate these numbers, add noise and other things to make the model much smarter. Because essentially, some of these, you just can't collect all these variations. So you actually need to increase the number of data. So basically, all these techniques, which I showed you on the right here, it takes our data set, transforms the MNIST data set from the very centered, nice data set on the left to this highly skewed, highly rotated and stretched data on the right, which gives us, starting with 60,000 characters of training data, up to 1.2 million characters of training data. And that makes our model much smarter. And so again, if the GIF played, you'd see that the number detection is actually a lot better. And you'd see the results showing that numbers are great. And so this is basically the code to do this sort of processing, this data augmentation or image augmentation. And this, as you can see, I can define ranges of angles and other things to stretch and change everything to make sure that I can add enough variation to make my model very intelligent. But now with letters, that's one thing. With numbers, that's one thing. But letters, there's many more letters than there are numbers. And so this is called the extended MNIST data set collected by Google, which allows you to add letters in terms of digits on top of digits. And letter recognition is a much, much harder task than digit recognition. You actually have to build a more complicated model and do a lot more things. And the convolutional model is still very useful and very important for this. GPT, all these big tools out there that you use, foundational models use ultimately convolutional and vision transformer models under the hood to do this. But the complexity of these models increases significantly with the intelligence you need to provide the model. So again, this is me attempting to, like, again, the GIF's not going to play, but you would see that as you're entering the digits as you're entering letters into the digit brain of the model embedded on the device, you would see all the letters are wrong. Digits would be correct, but the letters would be incorrect. And because it's, even with the letter data, it's still not smart enough to understand the variation just based on the intelligence for the digit model. And so we have to talk about how models learn at this point. And so this GIF roughly shows what happens when an AI is actually learning how to find a particular letter or something. It goes through its classification space using a loss function. This gets a little bit deep, so I'm not going to go too deep into this, but again, this is my research background coming out. This loss function creates this landscape of intelligence, and there's an algorithm called stochastic gradient descent, which allows the model to hone in on this space to find out where the correct letter is. So this is what's happening under the hood. If people are interested in what the AI is looking at, it's something like this, and actually quite fascinating. And this equation on the bottom, which is called the gradient descent equation, is what makes all AI work, the current version of AI. So if you want more info, come talk to me later. But essentially what we did, I took the model that I showed you before, which was a very small model, and I increased the complexity of this model significantly. I added many more layers. I added dropout layers. I added special types of layers. I added 3 levels of dense neural network layer to it, and I added many more hyperparameters, other things to the model to make it much more complicated. And essentially what happens is that's still not enough. You have to actually find the correct parameter space. So on top of that, there's a process called cross-validation, which allows you to search the parameter space for the optimal models. This is called stratified k-fold cross-validation. This is the code for this, and it allows you to find the best optimal parameters to make your model super smart. And so, again, this takes a lot of work, but essentially a lot more processing power, but the model achieved a 91% validation accuracy on the MNIST data set, as opposed to the smaller accuracy. And so again, the GIF might not play, but what I would say is that you can, on the actual other slides when I share them out, you'll see all of these GIFs that the letter recognition is almost perfect here. That on the crosswords, I can enter whatever letters I want, and then the letters get rendered in almost any variation, small, large, whatever. And the model's still pretty small. And yeah, and so before I get to the conclusion of my talk, there's this idea of synthetic data. So we talked about synthetic data. In the world of AI, for anyone interested, there's a theory of like mode collapse, where if you add enough synthetic data to the world, and since AIs learn on the data of the world, they will be learning on their own generated data. And at some point, all the actual intelligence will leave the data and create all the same characters or all the same collapsed modes, and there won't be any learning. That's a grandiose kind of theory. We actually wrote about that at the times, but the point is that there's nuance into that, and there's not, for models like this, any risk of that. So synthetic data is actually a very powerful technique in the world of machine learning and model building to actually create larger data sets for your model to be smarter. But the visual on the right is approximately what it would look like if mode collapse occurred on the system that I'm showing you right now. There's the article in case anyone's interested. And so the next steps are basically enhancing the model and doing things like adding strike to replace or strike to erase. We can do that because on Android, we have this whole concept of the Android Private Compute Core, which allows you to download more complex models and do on-device fine-tuning. Fine-tuning, I don't know if anybody's ever heard of fine-tuning here. If you're into AI, you know what fine-tuning is. That means that on the device, the handwriting style can be changed, so it can actually learn your particular handwriting style, and the model can change its intelligence. So even if you have a really crazy handwriting style, it will pick up what you're doing. And essentially, the advancements in that is that I showed you the convolutional model. We then moved to the vision transformer model, which is the current version of this model that can do much more interesting recognition. And so again, this is like, now the last caveat I would make is that all that we did was to essentially learn how the structure of machine learning would work on device. But if you use the digital ink recognizer that comes with Google ML Kit today, you can see that the model, without much work like what we did all those months ago, is needed because the recognition is actually really good. And it's not perfect, but it actually allows you to recognize different styles, different languages of letters, different types of characters, and whatnot. And so I put up a sample GitHub project for anyone who wants to try this out of how to do that. And one of the things that I normally talk about with AI is that you need to QA what happens in AI. So I also built the tool to QA any letters that are incorrect to make the model smarter. So if you want to re-download the model or improve the parameters of the model, you can use the QA tool on the device that I coded here to do something similar. And this allows us to do things like more advanced self-training. As you can see, it can find out which letters are more accurately or less accurately displayed here. And so basically, that's basically it for the talk as far as there's more detail and whatnot. But yeah, thank you.